In this video, I'll discuss surface forces. To make things more clear, I've decided to go from a generic two-dimensional triangular element to a very specific two-dimensional triangular element where I have three nodes. A node located at 1, 0, a node located at 0, 2, and my third node is located at 2, 2. I'm discussing this term here, the second term on the right-hand side of my stiffness equation. I mentioned in a previous video that this shape matrix is slightly different than the shape matrix in our body force term. How do I mean that it's different? The idea of my surface forces is that in three-dimensional space, not only can I have body forces along the length of a bar or a beam, but in addition to body forces that are located and distributed throughout the body, I could also have some force applied just along a given surface or a given boundary. Suppose I had some forces that were applied just along this top boundary of my two-dimensional element. I might have forces that each force along this length, which is distributed along the length, might change along the length of the surface. My force, my distributed load, could be some function of x and y. In this case, since I'm just along the surface, my y is a constant, but I could have some force that's dependent, that has an x component and a y component dependent on x. If I was along this surface, it could be dependent on both x and y, and if it was along this surface, it could also be dependent on both x and y, because x and y are changing as I move along the length of the surface. Since it's a surface, but it's a constant thickness, I can take this surface integral, which is an area integral, and because I know I have constant thickness, and since I know I can't have any z dependence, I can take this area integral and convert it to a thickness times a line integral. In this case, my x is the only thing that's changing since I've picked a top surface where y is constant. I'm integrating from 0 to my x-coordinate here, 2. So now I've gone from an area integral to a thickness times an integral from 0 to 2. I mentioned that this shape function is different, or shape matrix is different than the shape matrix I had for the volume integral. My generic shape matrices are of this form. I had this up in the last video. Notice that these various terms, n1, n2, and n3, are made of these equations where I have a linear equation in terms of x and y. In this case, along this surface and only along this surface, my y is a constant. So this n1 for this along this surface becomes n1 along the surface is equal to 1 over 2 times the area, alpha 1 plus beta 1x. But now, instead of gamma 1y, I know what y is. So this becomes gamma 1 times 2, because my y component is 2 along this entire surface. Likewise, n2s is 1 over 2a alpha 2 plus beta 2x plus gamma 2 times 2, where the 2 replaces my y component. If I was along this surface, then I would know what x and y were along the surface, but they would be either x would be dependent on y or y would be dependent on x, depending on how I want to think about it. So these are the same terms that I had in the body force term. But now I know more information about the form of these shape functions. Just like the body integral, this f of s, this is a double f of surface is a 2 by 1, where the first term is my x component of my body force as a function, as my surface force. It is a function of x, and in this case, I know y is equal to 2. Likewise, the second member of this matrix is the y component of my surface force. It is also dependent. It is a function of x, and in this case, I know y is equal to 2. I will do the same thing. I will multiply it by this matrix. I will get the same result, that I will end up with a force. The x components will only be multiplied by this column, which will result in my u equation, u1, u2, and u3. The y component will get multiplied by this term, which will correspond to my v displacements, v1, v2, and v3. All right. In our next video, we will very briefly discuss the point force vector, and then we'll move on to discussing forming a global stiffness matrix and a global stiffness equations.